This is lesson 59 of the Quantum Mechanics mini lecture series, Operators Part 4. So before I was the very last video, towards the end of the very last video, I mentioned things like column vectors and row vectors. So suppose I have these expressions here. So suppose I have this expression, I should say. So this quantum state here. To turn this into a column vector, all I do is simply rewrite it as follows. Okay, where the coefficient of this one state here is just 1. Okay, it's the same thing as writing like x. Okay, that's just like 1 times x. So that's how you go from one form to another. To turn this into the equivalent bra state, we need to turn the column vector into a row vector and take the complex, what's called the complex conjugate. Complex conjugate. Okay, whenever you have complex numbers, or whenever you have imaginary numbers like I, you need to take, so that means take the opposite sign, take opposite sign of a complex element, okay? So, for example, the I becomes minus I, right? Let me show what I mean. So this here, this state here, psi, can rewrite it as follows. So this is the bra equivalent, half. Okay, the 1, so we're going to write it in row vector form, minus I. So nothing happens to the real number 1, just the I. As an exercise, try and work out the bra equivalent of the following column vector. Okay, it's the same idea. And since a ket and a bra, they're expressed in different terms, in different ways, different mathematical ways, this implies that they're actually both very different mathematical objects. So ket vectors belong to what's called a Hilbert space, H. Okay, this is a state space. Okay, the space through which states act on, right? It's a vector space because we're dealing with vectors. And bra vectors belong to what's called the dual space, H with an asterisk. Okay, this is called dual space. Okay, and just a note in general, quantum states are basically vectors in a d-dimensional vector space over the complex numbers, okay, because quantum systems are very complicated. They can have a lot of variables. Okay, and H, the state space H, Hilbert space, is named after the renowned German mathematician David Hilbert. And it was actually later coined by the Hungarian-American mathematician John von Neumann. And what Hilbert space does, unlike ordinary space, the Euclidean space that we know of, it allows us to make use of as many dimensions of space as we like, even an infinite number of dimensions. That's why Hilbert space is also called abstract vector space. So let's now go a step further and talk about how we can describe a quantum system that's evolving. In other words, changing with time. The word evolve means change with time. Okay, because things change, right, over time. So a quantum system is basically a physical system that's depicted by a vector in a Hilbert space, okay? Okay, quantum system could be an object like an electron. We use a vector to describe it in a Hilbert space, H. And we can use the matrix representation of an operator to define the important idea of what's called a Hermitian adjoint, okay, which I'll define in the next video. But quantum systems, they evolve just like anything else, and we need maths to describe it.